All right, last thing I want to show you, and like I said, if you're tired of seeing me on video, I totally get it. I'm tired of seeing me on video, so you could totally can this and just save it for later. But if you want to, I want to just look at a situation that's not an elastic collision. So some really cool stuff we'll do. Like, for example, with 2D collisions, when you apply elasticity to it, you combine that with the Pythagorean theorem, you get a really cool thing about the fact that the particles, if they're equal masses, like how they come off. You could like predict not only the velocities but the angles, and that makes you really good at being a pool shark. So if you ever, when you go off to college and there's pool tables in the dorms, you know momentum, you could figure all this stuff out. Pooled ball collisions are almost perfectly elastic, and you could win money from your friends and family. So keep that in mind. Okay, so here's a simple situation, though. It's not what I just said. It's something different. Let's look at a ballistics problem, because this is a case where it's not necessarily momentum conservation that we care about. Like, we might want to be looking at multiple conservation laws in one problem, but it's a collision where energy is not conserved necessarily, but you might have parts of the problem that involve momentum conservation and part that involve energy. So I like to call these multi-conservation law problems. So a good example might be, in fact, let's use our elastic. Where are they? Let's not. We'll save that for class. Let's look at a situation where I have like a block, and it has a mass of something like 1 kilogram. Let's make it really straightforward. And let's say I have this piece of clay that's like hurling towards it, and let's say it has a mass of 0.2 kilograms, and it's hurling towards it at a speed of like, I don't know, 10 meters per second. Tires, I'm going to make up regular numbers, and let's say this is at rest. So they collide, and then let's say there's friction here, and let's say there's a mu k of 0.4, and I want to know, after they collide, how far will the system slide? If the clay that sticks to the block, how far will it slide before it comes to rest? So this is different, right? Because we know there's a collision happening at this like one location, and so we know just immediately before and after we're going to have Pi equals Pf. But then as we move from here to here, we have something different at play. We have an object that has kinetic energy, it's coming to rest, and there must be work done here. So here we have work-energy transformation, and we have to look at the work-energy relationship to figure out what's going to happen. So let's take a look, and I like to think of these sort of multi-conservation law problems as like play in a couple of acts. So we have the collision, which is like Act 1, and then we have the slide, which is like Act 2. And in the slide, we're going to be dealing with work and energy. In the collision, we're going to be dealing with momentum. So let's take a look at the situation. So first, let's do momentum conservation, which is going to happen at this location before the slide happens. So Pi equals Pf. My initial momentum is going to be the sum of the momentum of the things. So 0.2 kilograms times 10 meters per second plus 0 equals, now they're stuck together, and actually we'll prove at some point, or maybe I'll have you prove it in class, that if things stick, they're definitely inelastic. You can't conserve kinetic energy if the two things stick. You could just show it algebraically. You could plug in the momentum, write out the kinetic energy before and after, and show that there's no possible way that they can be equal. And that's kind of cool. So if they stick, automatically inelastic. It's not elastic. So our mass is going to be 1.2 kilograms because they're sticking, and then my velocity is unknown. So this is going to be 2 equals 1.2 v, and 2 divided by 1.2 is going to be 1.7. So I have this thing moving at 1.7 meters per second now. After the collision, I have like putty on the thing, and it's moving at 1.7. Now I'm going into an energy transformation. Let's think about, we know potential energy is not an issue here. There is no UG, there is no spring. But I have a Ki, I have a Kf, which is 0, and I have a force that's doing negative work. And since it's not a position-dependent force, I don't need to do any integrals or anything fancy over here, although I could have an integral, and that would be kind of fun. So for the second part, going from here to here, I need to, I want to figure out the distance it slides before it comes to rest. I'm going to use energy initial, or I'll write it out in our more formal way that we've been doing it. The work done by any external non-conservative forces is delta K plus delta U. Well, okay, let's do the work done by non-conservative forces first. Well, I know it's a frictional force, so the work is going to be mu K times the normal force, which is mg. Well, that's 1.2 kilograms times 9.8. 11.76 newtons is the normal force, times the distance, but remember it's negative because the angle between them is 180 degrees. So if I did my dot product, I'd have the force pointing backwards, the displacement pointing forwards. That's a negative work done by friction. That's going to be a delta K, which is K final minus K initial, plus a delta U that's non-existent because we don't have any height changes. So I could say 11.76 times 0.4 is 4.7, so negative 4.7 D equals K final minus K initial, which is 1/2 times the mass times the velocity that I just calculated after the collision. I can't use this velocity because I know the velocity of the assemblage after the collision is not the same as the first. So 1.7 meters per second squared. Notice my negatives work out. If you forgot that this was negative here, or you forgot the negative here, you'll realize that you can't just make it up and put it in. You can't do wishful algebra. You got to go back and say, where did I lose my minus? And you either lost it here because you didn't do the delta K right, or you lost it here because you forgot about the fact that friction's work is negative. And so if I just calculate this now, 0.5 times 1.2 times 1.7 squared, I divide by 4.7, I get that the distance is 0.34 meters. And that's how you combine energy conservation with momentum conservation. All right, everyone, have a great weekend. I'll see you on Monday. Bye.